this is your presenter Asloob Mudassar, and I am presenting part F of the slide number 142 of the course on laser physics. And this presentation is in continuation of the previous 142 slides with the different extensions. That is slide number 142 slide A, 142 slide B, 142 slide C, 142 slide D, 142 slide E. So it is recommended that you go through all those previous slides, different versions of slide number 142, so that you can easily understand this current presentation. So in the current presentation, I am going to present fiber lasers. In fiber laser, fiber is a single mode laser made of silica with the core doped with a rare earth element. So you see that here the doping is from some element from the rare earth elements, which will act as an active medium. Like a conventional single mode fiber, the pump beam is launched longitudinally into the core from one end of the fiber. This conventional single mode fiber has a central core surrounded by a clad material of a lower refractive index. In a double clad fiber, the first clad material is surrounded by a second clad material of even lower index. In case of a double clad fiber, the pump beam is launched into the inner, that is the first clad material. Diode lasers with high quality beam can act as an efficient pumping source for doped single mode silica fibers. So when we talk about in this lecture about fiber lasers, it means that we are talking about a single mode fiber which has been doped from a material from an element from the rare earth, and probably that element will be neodymium. And I am going to show you the fiber which is a double clad fiber. For example, over here you can see the caption of the figure is schematic showing coupling of a high power undiffracted limited beam from a diode into the inner cladding of a double clad fiber cable. So the coupling is being performed to the inner cladding of a double clad fiber system, which you can see that these arrows indicate that a high power pump beam which is being launched, which is obtained from a diode laser, is being launched into the inner cladding of the double clad fiber system. So you can see that here this is the internal core of the fiber, and then outside that one we have the inner cladding, and then outside the inner cladding we have the outer cladding. And the beam that is being launched is not diffraction limited. So it is mostly it is an undiffracted limited beam which is being coupled in this case. A typical single mode fiber has a core radius. Here we denote the core radius by A, lying in the range from 2.5 micron to 5 micron. So this is usually the range of radius for the single mode fibers. The transverse dimensions of the pump beam represented by WP and the output laser beam represented by W naught are comparable to the dimensions A of the fiber. A single solid state bulk laser device. So you see that here we are talking about solid state bulk laser device, not the fiber, but it is the bulk laser device, has a rod diameter much larger, and thus the pump beam diameter is nearly 50 times larger than that of the pump beam in the fiber laser. So the fiber laser diameter is very small. You can see that the range is from 2.5 to 5 micron, and can lie anywhere in between these two limits. So this is the diameter of the single mode fiber, and the bulk solid state laser that is being used to launch the beam into the fiber has a much greater diameter, nearly 50 times larger than the diameter of the pump beam in the fiber laser. So the fiber laser has a very small diameter, and the pump beam that is being launched into the fiber laser has a diameter much greater than that one, which is more than 50 times larger than the radius of the single mode fiber. The threshold pump power requirements, which is proportional to W naught square plus WP square, are thus reduced for a fiber laser by 2 to 3 orders of magnitude in comparison with the bulk laser. So you see that this is the requirement of using the fiber laser, that the requirement of threshold pump power is reduced by a factor of 2 to 3 orders of magnitude in comparison with the bulk laser. For typical fiber laser parameters, the threshold pump power below 1 milliwatt have been demonstrated. That is, the fiber laser have been demonstrated very successfully with a power below 1 milliwatt. Active medium in such a fiber can have low radiative quantum efficiency. You see that here you may encounter different terms in this presentation, and almost in all the presentations you can encounter different terms. For example, here we encounter quantum efficiency, and below that we have slope efficiency. For that one, you can type these terms on the YouTube search engine, and along with that you can write a laser physics course, and then you can find these terms explained in my relevant previous slides. So the active medium in such a fiber laser can have low radiative quantum efficiency. The short lifetime tau of the upper laser level is also affordable. Laser efficiency is independent of the upper state lifetime. Laser slope efficiency is independent of the upper state lifetime, which is tau. And you know that the slope efficiency will be defined by the rate of output power divided by the rate with the change of input electrical power to the diode system. So that will define the slope efficiency roughly. And for precise definition, you can search this term on the YouTube along with and write laser physics course along with that one, and then you can find relevant slides where it has been explained. And you know that this the figure that I have already explained, that this is a double core double clad fiber cable consisting of inner cladding and the outer cladding, and the high power is usually launched into the inner cladding of the fiber of the double clad fiber. Thus, a fiber laser, high slope efficiency and low threshold pump value can be obtained when the fiber laser is pumped with a diode laser. And the typical diode laser and the typical laser which is used and the typical diode laser which is used as a pump beam for the fiber laser is actually ND silica fiber or neodymium doped silica fiber. The pump absorption cross section at peak wavelength is sigma p, which is 2.8 into 10 to the power minus 20 centimeter square, and tau, which is the lifetime of the upper state of the diode laser, is 300 microsecond, which gives a pump intensity equal to IP equal to h nu p over sigma p into tau. And substituting these values for this, taking the wavelength from ND silica fiber, substituting that one in using the frequency nu p, which is the frequency from this silica fiber, and h is Planck's constant, sigma p has been defined, tau has been defined. Substituting these values, you can find out the pump intensity IP, which is nearly equal to 25 kilowatt per centimeter square. And the output power which is launched into the fiber laser will be given by, that is a P out will be equal to IP times I core, and this P out is actually the output optical power from the pumped diode laser, which is being coupled with the fiber laser. So P out will be equal to IP, that is the intensity from the diode laser, which is IP multiplied by the I core. That is approximately 0.25 milliwatt, where A core is equal to 10 to the power minus 7 centimeter square is the cross sectional area of the fiber core. And you know that the fiber core diameter has been explained earlier, that it lies in the range, that is the radius lies in the range from 2.5 micron to 5 micron. And using a value from that one, you can calculate the cross sectional area of the core of that of a single mode fiber, which is roughly equal to 10 to the power minus 7 centimeter square. The relationship for IP was obtained from the balance equation, and this is the balance equation, that is the absorption and the emission will be equal at the balance. That is why we write the balance equation. And on the right hand side we have the spontaneous emission, and on the left hand side we have the pumping equation, and these two rates are equal to each other, that is the absorption rate and the spontaneous emission rate will be equal for, and that is why we write the balance equation, and which is given by sigma p times fp times ng is equal to n2 time, divided by tau, under the condition that Ng is equal to N2, where Ng and N2 are the populations of the ground level and the upper laser level respectively, as in case of a 4-level laser system. So from here, substituting representing FP in terms of the intensity, we can find out this relationship which has been written over here. Or otherwise, you can search out this intensity. That is the saturation intensity. You can search out this intensity term on the YouTube channel, and you can find out this term. And for that one, you need to write laser physics course also, so that you can find out this expression very easily. Fp is the pump photon flux, assumed to be uniform over the cross-sectional area of the rod or the fiber core. Under pump power below 1 milliwatt, that is close to 1 milliwatt, more than half of the ground state population will be available in the upper laser level. It can be established that if the pump power exceeds the saturation power by a factor, say F, the power penetrates to the fiber by a distance F times the extinction length. And the extinction length for a fiber is defined by the parameter L, which is equal to 1 over alpha P, where alpha P is the small signal absorption coefficient. The output power of the fiber laser is limited by the power of the diode pumping laser. So the pumping laser, which is used to couple the optical power into the fiber laser, if that power is greater, then of course we can obtain a greater output from the fiber laser. So over fiber, the output from the fiber laser will strongly depend upon the power of the diode pumping laser. So you see that here I am using the pumping laser, which is used to launch optical power as a pump beam into the fiber laser. For maximum power coupling, the diode pumping source must have a diffraction limited spot size. So you see that here, if the spot size is diffraction limited, then of course maximum output power can be coupled into the fiber laser. And if we are using diode laser as the pumping source, if the spot size is not diffraction limited or is not round, then we can use appropriate optics with the output beam from the diode laser in order to make the spot size nearly diffraction limited. Single strip laser diode source along with appropriate optics meets this criterion of the efficient pumping source. That is, we can convert the output beam from the single strip diode laser into a diffraction limited spot size using appropriate optics with that one. And this has also been explained in one of the previous slides. High power diode lasers for pumping have poor beam quality. So this is a drawback of the high power diode lasers, that their beam quality is very poor and are appropriate to act as a pumping source for double clad fiber lasers. So if we want to use high power diode lasers where the beam quality is compromised, then we need to use the double clad fiber lasers. A single clad fiber laser with high power diode outputs will not work. Light from the pumped diode is coupled into the inner cladding material where it is progressively absorbed by the fiber core. In this way, effective absorption coefficient will be smaller than the core's actual absorption coefficient. To fully utilize the pump power, the fiber length can be increased till the propagation losses bring the pump intensity below the threshold intensity value. So you see that we can make the fiber length longer, that is the laser fiber length longer, so that we can get rid of the losses and the pump intensity below the threshold intensity value can be obtained. Multi-mode diode pump source. Multi-mode means that is the pump source contains not only a single length but multiple wavelengths are available for the coupling. That's why we call it a multi-mode. It means many wavelengths or at least a few wavelengths are present in such a pumping source. So multi-mode diode pump source, when effectively coupled to a fiber laser, gives an enhanced brightness monomode laser output. Under multi-mode pumping, two or more photons of equal or different wavelengths can raise the ground state population to even higher states with the lasing photons greater than with the lasing photons greater in energy than the individual photons added together to pump higher states. So you see that this is the advantage of using a multi-mode fibers, that different fibers, that different modes in the pump source can be available to pump the ground state of the fiber laser to even higher states by combination of these photons. That is through up conversion process. Higher states can be obtained, that is the higher population in the higher states can be obtained, and then the lasing photons will have can be obtained with energy greater than the energy of the individual photons added together. So let me read again that under multi-mode pumping, two or more photons of equal or different wavelengths can raise the ground state population to even higher states with the lasing photons greater in energy than the individual photons added together to pump higher states. Emission of laser in this way is referred to as up conversion laser, which is illustrated in figure number 7. So this is figure number 7, and the caption is schematics of an up conversion lasing phenomena. You see that this is the ground states of the fiber laser, which is being pumped with a multi-mode laser, for example, containing three different pump frequencies. So the first pump frequency, for example, will raise the ground states to, for example, this level, which has been shown through the pump 1. Then the pump 2 can raise it further, and the pump 3 can even raise it further to the highest possible level. So the other levels are also achievable, but here we are just talking about that our multimodal laser contains only three different frequencies, so we can raise up to three different steps, and this then forms the upper laser level. So the upper laser level will be raised ultimately by the final pump 3, and then the lasing action will occur between the upper laser level and the lower laser level. So the lasing action uh, will will be processed between these two levels. So emission of laser in this way is referred to as the up conversion laser, which is illustrated in figure number 7. Non-radiative decay of the levels involved in the up conversion through the process of a multiphonon deactivation can limit the process of up conversion. So you see that here I have shown the up conversion process, but you know that these can also decay through non-radiatively. That is, we can go back to the previous, to the lower states through non-radiative decay by phonons, by phonons, and to avoid this, which should be avoided. So the non-radiative decay of levels involved in the up conversion through the process of multiphonon deactivation can limit the process of up conversion. The non-radiative decay rate is proportional to the number of phonons generated in the process and to the energy of these phonons. So you see that non-radiative decay, which we want to avoid, so that we can have a maximum population inversion in the upper laser level. To avoid this non-radiative decay, which is dependent upon the number of phonons, we can use those materials as the dopant materials, which can produce less number of phonons and with weaker energy of phonons. Under that condition, we can minimize this non-radiative decay. So the non-radiative decay is proportional to the number of phonons generated in the process and to the energy of these phonons. Now, how we can decrease the number of phonons created and the energy of these phonons, so that we can have up conversion unaffected by the system, and so that we can get we can get a greater population inversion in the upper laser level for intense beam from the fiber laser. So the remedy, or that is the two problems that has been raised in the previous paragraphs, that is the number of phonons and the energy of these phonons. So if we reduce the number of phonons and the energy of these phonons, then we can avoid the non-radiative decay, and we can avoid disturbance to the up conversion process. The rate of non-radiative decay can be reduced by choosing host material with lower phonon energy, such as a mixture of heavy metal fluorides. So you see that rather than using different dopant materials, and you know that the dopant materials that we use are from the rare earth elements. So if we use the same dopant materials, then we can choose a different host material. So the rate of non-radiative decay can be reduced by choosing host materials with different phonon energy, such as a mixture of heavy metal fluorides, also known as Zablan. Z stands for zirconium, B stands for barium, L stands for lanthanum, A stands for aluminium, and N for sodium, and N for sodium. Zablan fibers, when doped with Tm3 plus ion, thorium triply ionized ion, and pumped with the three identical phonons, with the three different identical or different photons, produce efficient up conversion laser in blue with a wavelength of 480 nanometer with an optical power ranging up to 200 milliwatt. So this was the brief introduction about the fiber laser. And you know that here the rare earth element will act as the active medium, and the host material is silica. And if you are using a Zaplan fiber, you can have different material as the host material. For example, the host material could be heavy metal fluorides. So this has been explained, that is the fiber laser has been explained briefly, and this is the end of part F of slide number 142.